kind of update. So now we are going to look at groundwater. Remember we talked about how we are dividing water into 4 topics really. Last time we talked about surface water bodies, and then we talked about surface water pollution. Today we're going to talk about groundwater bodies, how groundwater moves, what groundwater is, and then we'll talk about groundwater pollution. And I'm going to take groundwater pollution from a slightly different tack, and that is, instead of telling you what they are, organic, inorganic, and we talked about that last class, I will tell you the sources from which they come. And these really are interchangeable in terms of, from where they come, surface water and groundwater, it all comes from the same place. So you have this treatment of what types of pollution get into water, and then we'll talk about how they get there. So this is the picture we saw last time, and we talked about the different reservoirs. And remember, we looked at volumes of different things, and groundwater really is the most important reservoir with regards to fresh water on Earth. Remember that if we just look at fresh liquid water, it's 99.75% of all water on Earth. So we'll look at it a little bit today. It's something that, just kind of to say as a side note, there are, whole courses on this, several courses. I teach 3 courses on groundwater stuff. And it's really difficult to conceptualize groundwater. It's really difficult to kind of describe it and to learn about it in an introductory class because it's all math, it's all calculus. Because when you're looking at groundwater, you have to drill a well. And drilling a well around here costs between $6,000 and $10,000, and that gives you one data point. And so if you have a study area, whether it's the Boston College campus, whether it's all of Boston, whether it's some job site where there's contamination, you have to pick the smallest number of wells you possibly can to tell the story that you need to tell. By training, I'm a groundwater geochemist. That's what my PhD is in. And it's an art. You're telling a story based on very scant data, and you tell the story mathematically. So you maybe can drill 3 or 4 wells in an area the size of campus even, and from that you have to interpolate what goes on between the points, both from a geologic point of view, so you know how fast water moves, and then also from a water supply point of view. So it's all math. I'm going to take the math out for the purposes of this class, but it's pretty high level math. So the zones in the subsurface, we talked about agriculture last unit, and we talked about the soil zone. We talked about soil moisture, and we said how half of the space between the grains is filled with air, half is filled with and water. That's the zone of aeration. You also know of it as the soil zone. That's not a place where we can draw water from because the air and the water mixing in between the two of them makes it unavailable for pumping. So then you have the zone of saturation, and you see from this picture, that's the area where the spaces between the sediment grains are 100% full of water. It's all water. That's where we can take water from. And the dividing line is called the water table. It's a 2-dimensional surface where the pressure from above equals the pressure from below. So its pressure equals to 0 is the definition of the water table. And the pressure from above comes from the atmosphere. The pressure from below comes from the water that's moving underneath the water table. All water is moving. It's all under pressure and it's all moving in the zone of saturation. That's groundwater. So those are the 3 zones, and again, we talked about them in a cursory sense when we talked about agriculture. There are 2 types of aquifers. I don't know offhand, I forgot to look this up, if your book makes mention of a 3rd type called a perched aquifer. You don't have to worry about that at all. The 2 types of aquifers that we talk about in the groundwater industry and in this field are unconfined and confined. Unconfined are what you just saw in the previous slide, where it's open to the atmosphere. It's sand or silt or some sort of fracture flow, some sort of situation where there's no confining layer. And so here we have water connected to the surface. There's the unsaturated zone and then the saturated zone, and you see that it's filled with water below a certain depth. Remember I said everywhere you go on Earth, you dig down deep enough, you'll have groundwater. Unconfined aquifers are really easy to work with because you know where they are. They're all open to the surface. They're actually quite difficult to mathematically model because one of the first things you need to know in an aquifer to do modeling is the thickness of the aquifer. And as soon as you start pumping it, you change the thickness. the saturated thickness. So it becomes this iterative, pretty high level calculus stuff. So really easy for us to work with, but difficult for us to mathematically model relative to these. And these should seem familiar to you from our discussion of oil and gas and traps. So in a confined aquifer, you have water that's sandwiched between impermeable layers, or layers that are unable to or unwilling to permit water or any sort of fluid to move between them. We looked at traps, right, when we looked at oil and gas, and we said that unless there's some sort of trap, unless there's some sort of impermeable boundary, clay is a good impermeable boundary, that's what we seem to have here, clay makes shale. You have water that is open to the surface in one spot, and so in that one spot you could consider that a local unconfined aquifer. But then you have the water sandwiched between these two layers of impermeable material, and so the water's under pressure. And so that's what artesian pressure surfaces are, potentiometric surfaces. This is always funny to me when you buy bottled water. They use artesian water as sort of a marketing ploy to make you think, oh, this must be fabulous water. You can put raw human sewage under artesian pressure conditions. It just means it's under pressure. So don't be fooled. So you have water under pressure in this confined aquifer, and these labeled A, B, C, D wells are wells that have been poked through the impermeable boundary, and so you're essentially releasing the pressure in that point, and water will rise up. We'll look at in the next slide something called hydraulic head, which is simply the level to which water will rise in a well. It will rise up some distance above the surface of that confined aquifer. So if you didn't poke through, the saturated zone begins here, but if you poke through, you can see that water rises up some level above the aquifer. And in fact, B and D, you have free-flowing wells. So you poke in the well, and the outlet of the well is beneath the pressure surface, beneath the artesian pressure surface, and so you have water that's free-flowing. These are easy to model because the saturated thickness never changes, but they're more difficult to predict. So if you're miles away and you decide, oh, I'm going to drill for groundwater here, you don't necessarily know this whole mapped out area, and you don't know if there's some contamination going on over in the recharge area. So yeah, bottom line, you have ones that are under pressure, ones that are not. The ones that are under pressure, really harder to predict what the quality will be without testing it regularly. So we said that water that is in the ground is all moving. It's all moving, and it's moving from high hydraulic head to low hydraulic head. This is where, the sort of element of math that we discuss in hydrology. Hydraulic head, in a field sense, is simply the level to which water will rise in a well, in a piezometer. So you put in a well, and I'll show you how you construct a well, and then you put in your water level measure, and it beeps when it hits water, beep, and you know that's hydraulic head. It's the level to which water will rise. Hydraulic head mathematically is a combination of the pressure of the overlying water, of the elevation above a datum, and then the velocity of that water. So you don't need to know that, but those are the three things that go into this. How high is water going to rise? And it's called hydraulic head. Essentially, water moves from high pressure, P stands for pressure, to low pressure. And so what you're seeing here, you can't ever obviously really scrape off the surface of the unsaturated zone. What you see here is that there is a river system, and you have high points on the landscape, and then you have low points. And what we typically say about groundwater is it's a subdued replica of surface topography. So what that means is that the highs aren't as high, the lows aren't as low. So you see that groundwater is doing, if you pull off the unsaturated zone, the same thing that the land surface is doing, but again, the high is not as high in the highest point, and that is a recharge area. Water is going down from the land surface and recharging the groundwater. And then the lows aren't as low, so water is discharging up out into surface water bodies, whether it's the lake in the back corner of that diagram or whether it's the river. Kind of cool if you think about it. The Charles River, if you've been to the Charles River lately, there's a huge amount of water in there. It's flowing constantly. We haven't had rain in a long time. So you might wonder, maybe, where does this water come from if we haven't had rain in this drainage basin for a long time? The answer is that in temperate regions such as ours, 80 to 100% of water in rivers and lakes and streams comes from groundwater. So in the fact that groundwater is always moving, it's going through the subsurface and it's discharging up out into the surface water, and then it will drain away ultimately into the river. So the point to this is that all water's moving, it's under pressure, and it's flowing from high pressure to lower pressure. And again, when we mathematically model this, you can get into great detail about the speed and the distance and vectors and all sorts of things. Cursoring from a field point of view, we measure groundwater, whether it's quality or the hydraulic head. We can measure a lot of different things about water with something called piezometers, which are really, really small diameter wells. The reason we use small diameter wells is because the larger the diameter, the more expensive it is to drill these. So you want to drill the smallest well you possibly can because that's cheap, and then maybe you can put more wells in, or just at least save your client some money. And the way that you drill them is you have this drill rig come in, and it's got a boom on it, and it raises up, and there's this, it's called a hollow stem auger. It's like a big corkscrew, like if you're unscrewing a bottle of wine. It screws down into the ground, and it's hollow, so the sediment comes up into it, and you keep pulling that up, and you look at the sediment, and that enables you to tell a lot of things about how water would flow through that particular material. So you drill down till you get to wherever it is you want to stop, and that's a big art to that. Where do you want to stop depends on what question you're asking of the system. But you drill this big hole, and then you put in the piezometer, which is simply PVC pipe. It's like that white plumber's pipe. You put that in, and you have screened it at a certain length and a certain amount. You screen the well based, again, on the question you want to ask. If you're just looking at where is the water table, you might screen that whole thing because water table is fluctuating, and you want to hit it wherever it is. If you're looking at contamination, and you want to say, okay, there's a gas station that's leaking, where is the gas going to and how much is there? Gas floats on top of water, so you'd make sure this is essentially on top of the water table. So you can go into great detail about this, but the width of the screen, the length of the screen, and how deep it is depend on the questions that you ask. So you put in the PVC pipe, and then you put in a bunch of sand, this labeled filter pack here. The sand is so that you don't have fines coming in and clogging the well intake. And then a bentonite seal, that's a kind of clay, and you're just excluding rainwater. You don't want rainwater to come in here because it can make hydraulic head higher than appear higher than it actually is. Or if you're looking at contamination or water supply, if you have rainwater come in, it's going to dilute the signature of the chemistry. So if you're looking at a contaminant plume and it's really contaminated without bentonite seal, you would dilute it, and you might say to the EPA or to your client, oh, it's no problem, it's not a lot of contamination. Then you put in this annular shear, just dump some of the dirt back in and put a surface seal, which is usually concrete. And then you have a well cap and a cover. And this enables you to do all sorts of things, like figure out where hydraulic head is, what are the seasonal changes, what sorts of chemistry is in there, and how does the chemistry change. So you can figure out, is there a contaminant plume coming in your direction. From the surface, they look like this. And I'm showing you this, setting you up really kind of for the talk I'll give on Friday, because we'll use a network of these wells in that talk. They look like little manhole covers, about this big. And you have a lock and a cap on there. Then you take, I should have brought one of these in, but a water level meter, and you drop it down into the well, and when it beeps, beep, you know that's where groundwater is. So it's one of the things that you do. But we try to do as few of these as possible, and then try to mathematically interpolate between the points to see what's going on. So as with surface water, we have two problems. One is water supply, and the other is water contamination. Water supply, we said that groundwater is a vast, largely untapped reservoir of fresh water in many parts of the world. However, it is possible to use it up faster than it can be replenished. Remember, we're not losing water. There's not a question of a water shortage globally. It's just that if water will come back into this area more slowly than the rate at which you pump it out, then you can have something, as you can see here, called a cone of depression. So we have three situations here. We have pre-industry, pre-agriculture here. The water table is doing exactly what the land surface is. Then you come to here, you have agriculture. You've drilled a couple of wells. The major well is maybe bigger diameter, it has a higher pumping rate, and it goes deeper down into the subsurface. It's not in the second picture being pumped at the maximum rate. But the minor well, which is not as pumped as hard and it's not as deep, can draw water. Now we have this change where you have a city that's drawing huge amounts of water, and you end up drawing a maximum cone of depression that causes your minor well to run dry. So you've caused this cone of depression. So this can happen. I don't know if I told you about USA Springs in New Hampshire. Yes, did I? No. So this is an intersection of really law and environmental things in New Hampshire. They have very lenient laws for industry, trying to draw industry to New Hampshire. And so these, I don't know if you call them unscrupulous, these bottling companies buy up a very small parcel of land, maybe an acre or something, put in a giant deep well and pump the heck out of it. And what is New Hampshire known as? The what state? Granite state, right? So it's not sand, it's not an endless supply of water, it's fracture flow. The granite has to have cracks in it. And so those wells are quite low yielding, maybe 2 to 3 gallons per minute. And that's okay because New Hampshire is not this major metropolitan area, and everybody has their own wells. Most people have their own wells, and so they can draw plenty of water. But when these companies, the last one that I was reading about, USA Springs, which is a shell for Dasani, come in, buy an acre of land, and start pumping the heck out of the wells there, then the residents' wells can run dry because you have a huge cone of depression. And it's interesting because the landowners will then sue USA Springs saying our wells have run dry, but the state is very careful to try to balance being pro-industry, bringing money into the state with the concerns of the homeowners. So these things can get quite contentious, and the state hasn't really come to the aid of these landowners who have no choice, their only source of water, but to drill deeper and deeper and deeper so they can get beneath the cone of depression, which can extend quite deeply. And you might imagine that when you're drilling through granite, it's very, very expensive and time-consuming. So that's the situation with groundwater supply. There's plenty of it, but it's possible to use it up faster than the system will naturally recharge. So now we'll look at the sources of contamination, everybody's favorite topic. How do you make groundwater dirty? So I have a list of things. This is just the first one. This is a septic system. Sorry, the bullet got buried. Septic system. Anyone on septic? Here? A couple people? Yeah. There's always some fun. Yeah. So septic systems are on-site wastewater treatment plant. We in Boston have a state-of-the-art wastewater treatment plant called Deer Island, and I'll show you a picture of it later. But when you have a lot of land, you're in a more rural area, and it doesn't make economic sense to sewer that area, people have their own on-site wastewater treatment plants. And these work really, really well when properly functioning. So what you have here is a house, and you have the PVC pipe, plumber's pipe, coming out of the house from your toilet, from your shower, from your washer, dryer, from your sink, from everything. And it comes out into this big concrete tank called your septic tank. And it's populated with some bacteria that enable the system to break down solids into smaller pieces fairly rapidly, also grease, things like that. So it goes out to the septic tank, and if you want to make a lot of money, be the person who goes into that manhole and cleans out septic systems, because it's not a pleasant job. So then you have this non-perforated pipe that comes out to a distribution box, and now you have all of this PVC pipe again, but it's slotted now, so there's holes in it all the way around. And it's sitting in a bed of gravel, and that helps the water go away from the system. So when you flush your toilet, when you use the shower, whatever, it comes out and it goes into this field called a leach field. This is all going on underneath your grass, and the water will leak slowly to the subsurface through the unsaturated zone into groundwater. This is actually a great way of treating water because of all the microbes. Remember we talked about the soil zone. The microbes that are in the unsaturated zone love nutrients. They love soap. They love nitrogen. They love all sorts of things that we get rid of in our septic system. So you have, in Mass, we have a 5-foot minimum regulation. Otherwise, you have to do a mounded thing, put it up on a little mountain. And the water goes through the unsaturated zone, and by the time it hits groundwater, it's clean, long as it works okay. Sometimes, though, in the spring, water levels are really high, and so then you're ending up with your sewage going right into groundwater, and if it hits groundwater, it's not going to go away because groundwater is anoxic. There's no oxygen in groundwater, and so there's nothing to break it down. So you want to make sure you have this 5-foot of unsaturated zone. The grass always grows really greenly beneath the septic system. And again, when properly functioning, they work well. Another little fun fact, the Cape Cod is essentially 5 big piles of sand. And water flows really quickly through the sand. And, oh God, these numbers escape me. If someone is from the Cape and knows these numbers, let me know. The population has these wild swings on Cape Cod. So I think, don't quote me on this, but I think it's something like in the summer, the winter it's 60,000, and then in the summer it gets up over 300,000. So the problem with putting people on a septic system is on a sewer system, is you build a sewer system, a wastewater treatment plant, for a certain population. You can build it for 60,000, or you can build it for 350,000. You can't build it to do both. Because what that means is that if you build it for 60,000, it's going to work well all winter, but then when the people come, obviously it's going to overload the system and you're going to have problems. If you build it for 350,000, then it's not going to work all winter. You have to pour lots of water in to get it to process, super expensive and wasteful. So a lot of people, most people are on septic on the Cape. But because the material is so permeable, water flows so quickly through there, the scientific number for how much land people should have to have a properly functioning septic system that doesn't go into other people's groundwater is about 4 acres. And those of you who know anything about the Cape, how many people have 4 acres of land? So regulators have arbitrarily said, oh, we're just going to say 1/4 of an acre. It has nothing to do with science. So everyone down there is drinking each other's septic water, and it's gross. Yeah, because they're all on wells, too. A lot of them are on wells. So really bad situation with septic systems when they're implemented. There it is, septic systems. When you have a septic system, typically you also have a groundwater well, and nobody is looking over your shoulder to make sure that you're supplying yourself with fresh water. So I just put this up quickly or briefly to show you that the textbook way of doing things is you have a gradient on the groundwater. You put your septic system down gradient of your well. So you're drawing clean well from your well, and then even if your septic system is improperly functioning, it's going down gradient. Water will never go from low to high head. But what happened here is, perhaps unbeknownst to these homeowners, somebody put in a deep well up gradient somewhere, reversed the flow, and so now the contaminated water from the septic system is going directly into your well. That can happen in many different cases, many different reasons. So you have to be aware of basin changes, and you should always make sure if you have a groundwater well that your water is tested, ideally quarterly, but at least once a year. So here are a couple of other ways that groundwater get contaminated. Everyone is contaminating groundwater. It's going on all over the place all the time. So there's a couple of other pictures here, but in terms of this diagram, you see some things going on. You see land spreading or irrigation. That's the agricultural stuff we talked about before, whether it's pesticides, herbicides, or spreading cow manure onto the land to try to get it to attenuate. You have dumps, which we talked about, dumps or landfills. And you have surface impoundment, so some sort of surface situation where there's contamination leaking into the subsurface. So these are several ways in which groundwater can be contaminated, but look what's going on here a little more deeply. At the surface, you have a unconfined aquifer, and so it's fresh groundwater, but it's highly polluted, right? From all the things that are going on at the surface, you also have some underground storage tanks that are leaking, ruptured storage tanks that are leaking, so you would never want to drink that water. But you have a confining area, so you have a layer of shale or whatever it is. You have another fresh aquifer here. It's not in hydraulic connection with the surface, and so that water could be quite clean. So if you're looking at this from a geologic point of view, you could have the most disgusting, toxic, polluted stuff going on at the surface, but if you poke through an impermeable layer, it's possible to right there get plenty of fresh groundwater. Then you have a confining layer here, so you have a third aquifer, and this aquifer is brackish. What that means is that it's salty. And so you would never draw it for municipal water supply. So what's going on here, somebody has an injection well injecting liquid waste, whether it's radioactive waste, whether it's the waste from an agricultural region, whether it's the waste from a human wastewater treatment plant. discharging that into an aquifer that's naturally poor quality. This was probably formational water, so it was formed in the ocean and the ocean water is still there, is actually considered a safe, sound practice. We're not going to drink that water. It's really deep. It's not ever going to come up. It's been down there for hundreds of thousands of years. So it is considered okay to get your pollution and inject it down into the subsurface. Another picture just to kind of harken back to the farming stuff that we discussed. Many ways in rural areas that groundwater gets polluted. You have the land application of all of those chemicals that we discussed, and we'll talk about them again. Road icing, so de-icing rather, so salt. Lots of accidental spills from roads and from trains. People spill things on purpose, so you have people dumping, I don't know, used oil, antifreeze, things like that when they do things with their car, dump it right into the ground. You have underground storage tanks that are leaking. Last statistic I heard is that 1 in 4 gas stations have underground storage tanks that are leaking in Boston. So you have all these things leaking into the subsurface, and you have an abandoned oil well here. So here is saline water. All of the oil has been pumped out, but that's now coming up to the surface and leaking brine into the fresh water. So again, lots of different ways in which we can pollute groundwater, and we do pollute groundwater. Anything that's going on at the surface, because of water's high polarity and dielectric constant, it will get. I think that's on there. Yeah. Okay. So this is again just a recap of what was in the previous slide. Any open dumps, rainwater will fall, pick up the chemical signature of the open dump, and pull it down into the subsurface. Landfills are quite safe relative to open dumps because remember we have a liner now on this system, and so hydraulically you disconnect it from the surface. Residential disposal, people pouring paint thinner, people pouring used oil onto the grass in their backyard. It's a common pathway for groundwater pollution. And then surface impoundments. It used to be, and we didn't talk about hazardous waste a lot in class in the interest of time, but it used to be that we thought disposing of hazardous liquid waste was okay in just digging a pit. So maybe some of you know about Love Canal. I won't talk about it too much now, but this gentleman tried to dig a canal through the Great Lakes, and he failed. He ran out of money, so he sold it to Hooker Chemical Company, who was dumping really hazardous waste into this surface impoundment, and then capped it, and that then leaked really, really toxic stuff into the subsurface. And a lot of people got sick by drinking groundwater from this. It was the beginning of the Superfund Act. Today we have something like this, and I believe I've showed you a similar picture before, not to put too fine a point on it, but hazardous waste is known to be quite dangerous, as you at least had a cursory treatment of in the last unit before agriculture. Carcinogenic, mutagenic, teratogenic, all sorts of horrible things go on when you're exposed to a lot of these toxic chemicals. So we have a very, very sophisticated system that's well above groundwater. You have this big concrete curve system with these drains and a clay dam in there, and you have very, very, very careful monitoring monthly of hazardous waste disposal facilities most of the time. Again, politically, this is tough though, because people open up a hazardous waste disposal facility and they can make a lot of money accepting people's waste. BC gives waste. Any school that has a chemistry lab, anything like that, there's a lot of waste that you have to pay a huge amount of money to dispose of this. And so these hazardous waste operators will make a lot of money accepting waste, but then when the land is full, when their hazardous waste landfill is full, they stop making money. And so what they do is abandon it, just go somewhere else, close that company, start a new company, and it can get to be really hard to track. And then the government has to be in charge of trying to figure out what to do with these. So there are abandoned hazardous waste disposal facilities everywhere. It's really difficult to regulate people. Why would they want to keep, staff there and make sure that everything's clean once they're no longer making any money? Picture of a landfill. Those were outlawed in 1991. They're just digging a hole and putting your municipal garbage that we've discussed in there. And I think I said this again. Apologies if I haven't, but the Fresh Kills landfill is in Staten Island, and it is a big landfill, and it was just dumped into a wetland. So there was no liner at all, and there was a big outcry in New York City saying, we have to get rid of this, oh my gosh, we're polluting ourselves, we're poisoning everything. So there's a big study undertaken to figure out what's going on with the Fresh Kills landfill, which is now closed. It closed before 9/11, but then they opened it again to take some of the refuse from 9/11. Big, huge study that was actually mandated by Congress to see, are we poisoning ourselves? And there was a lot of water samples taken, and it was found that, yes, there's elevated levels of things, but they were sodium, chlorine, calcium, and sulfate, which are the 4 highest constituents of seawater, and the water is going from the landfill directly into the ocean. So it was pretty much the same chemical signature of seawater. So again, landfills in the great scheme of things, not a horrible, huge environmental problem. There's a picture of a landfill cross-section, and what you can see is that there's all sorts of layers, membranes, geotextile, so that hydraulically you isolate it from any rain that falls. You can recover the methane, and you make sure that you pull the leachate out that you can collect and treat well. So those are landfill cross-section. Yeah. Yes? Okay. Yeah. Okay. A couple other things that happen. These are all kind of fun too. Mine tailings. We've already talked about this. So again, you're seeing these connections. When you mine for something, you're putting huge amounts of mine tailings on the surface. You have a big open pit. Water, rainwater will fall, pick up the chemical signature of whatever it is you're mining, whether it's radon or arsenic or cadmium, whatever you're mining, and go into the subsurface. Material stockpiles. So like the DPW stockyard, when they put huge amounts of road salt sitting on the surface waiting for the next snowfall, water will pick up that chemical signature, put it into the subsurface. Graveyards. Here's a picture of a graveyard. It used to be that graveyards were considered park-like, and so you'd go out to the graveyard, bring your picnic lunch, and you'd commune with Aunt Mildred, and you'd have a nice day of it. And they were on the high points on the landscape, so they were up in the hills. And that wouldn't be so bad, except for the fact that historically we used arsenic as an embalming fluid to embalm the bodies, and you're on a topographic high on the landscape. That means you're in a groundwater recharge area. So whenever it rains, the water's picking up the chemical signature of the arsenic, plus any bacteria, viruses that the deceased were made ill by, any sort of organics, and dumping it out into the rivers and the low points. So wherever you have an older graveyard on the landscape, I guarantee you have an arsenic problem in the river down gradient of the graveyard. Similar animal burials. So if you remember, there are a lot of sort of premature deaths associated with the agricultural industry. Those go into big mass graves that are unlined. You don't have to line them according to our regulations. So same thing, water comes through, picks up the chemical signature of all those dead bodies, the little male chicks and the downer cows, etc. That goes into groundwater. Or if you have pets, companion animals, that you didn't get incinerated and you have in a little urn, big mass graves for companion animals as well, picking up the chemical signature of those, dumping them into groundwater that will eventually dump out into surface water. So just to finish up with a couple of more slides, I showed you a septic system. In Boston, we have a water treatment plant. Most people, it seems from a show of hands, are on some sort of water treatment plant. This is where we put water so that it doesn't contaminate the water that we drink. So when you take a shower here in Boston, the water goes out in these pipes under the road. Sometimes they're pumped up a little, and then they're gravity fed out to Deer Island, where if you've ever flown into Boston, you see these big, huge egg-shaped digesters, big spheres, and those are methane harvesters. In an attempt to get the plant to generate its own electricity, it takes the methane out of the waste. So you have the water coming in. You have a bar screen right here, and the bar screen will filter out big things like sticks, branches, things like that. And then a grit chamber. Remember I said that taking the sediment out of water removes 98% of the viruses and bacteria. So it looks like a big giant swimming pool, and you just let the water sit, and the sand all settles to the bottom, and taking with it a lot of the chemicals and the viruses. And then you go into a settling tank, another big chamber, and it sits even longer. And the sludge, so like solid waste from humans, goes down to the bottom of the settling tank. Then you have a sludge digester. Next, you have an aeration tank, which is like a big swimming pool, but like a spa. All this air is being bubbled through, and that gets more of the things that are organic and other chemicals and things in the water to complex. So you put it into another settling tank, and you have more sludge generated. You put the sludge into the digester, and now you have the last tank where you put in chlorine sometimes, or you can expose it to ozone or something to try to get rid of any last bits of viruses or bacteria. You have a huge amount of water that now has to discharge into lakes, rivers, oceans. If you're in a really landlocked area, you would drill a groundwater well and discharge it into the subsurface, because you don't want huge amounts of water just pouring over the surface. The sludge, remember we talked about how in Massachusetts it is not legal to use this on agricultural land, right? It's a valuable nutrient. It's not legal to use this in agricultural land unless you're feeding the products of that agriculture to animals. So what we do in Boston is we take that sludge and we put it onto rail cars. We ship it down to Florida and put it on the oranges down there. So that's how your orange juice is fertilized, from the waste, in part at least, from Deer Island. Boston historically was, I started to tell you about this, one of the most polluted water bodies, Boston Harbor, in the world at the time, the 1800s. Because we were discharging raw sewage, and lots of it, into the harbor. Then we created Deer Island, which is a state-of-the-art wastewater treatment plant. So all of that stuff that I just showed you goes on, but then you take the water, still elevated in nutrients, and it goes down to the bottom of the Boston Harbor. It's a 420-foot shaft, goes down to the bottom of the Boston Harbor, 24-foot diameter pipes. It's a huge pipe. And then it goes almost 10 miles out of the Boston Harbor, out into the Atlantic Ocean. The last 1.25 miles, the pipe gets smaller diameter and it's slotted, so you have a more diffuse release of our waste, because there is still some nutrients in it. You don't want to have this toxic load coming out of just the end of a pipe. So that's where your waste goes. It goes out to Deer Island, gets treated, goes out into the Boston Harbor. What we're seeing, however, is that we are doing a good thing in Boston. We turned Boston from one of the most polluted water bodies in the world, again at the time, to one of the cleanest urban water bodies in the world. It's a really good news story. Things that we didn't think would come back within several generations, seals, all sorts of fragile marine life, came back into the Boston Harbor really quickly as a result of us cleaning it up. So the Boston Harbor is a very clean place to be. The problem is you have the outfall, right? So the outfall, think of Boston as like my ear, this pipe coming out of here. And then you have the Cape. And the water system is such that it swirls down around the north shore of Cape Cod. The yellow and the darker colors are not pollution, it's simply the depth. What you see is that a lot of this is super shallow. Because it's super shallow, the algae that's sitting there is now going crazy, eutrophying, in the face of all of our elevated nutrients from Boston. So we made our harbor clean, but the water comes and swirls down on the north shore of Cape Cod, and also Stellwagen Bank, which is a fishing ground, place to see whales, and you have massive problems of nitrogen pollution. Nitrogen is causing the algal blooms, then the algae die. Remember we talked about eutrophication. You rob all of the water of oxygen, you rob it of light, it starts dying, senescing. It's a really kind of gross situation on the north shore of Cape Cod because of us. Last little bit, we are very lucky. We have very clean drinking water. Many places, especially in developing countries, that have up to 100% the darkest color of no access to safe drinking water. It's a big initiative these days, right, to try to provide developing countries with safe drinking water. And just to let you know about, this whole bottled water versus tap water thing. The bottled water industry, especially in the 90s, early 2000s, did a great job of convincing you that tap water is horrible, it's unsafe, it's gross, it's really bad. The reality of the situation is that tap water is about as safe as it gets. In the United States, the United States EPA, or Environmental Protection Agency, has implemented a really all-encompassing list of MCL, maximum contaminant level. And then MCLG's maximum contaminant level goals. That's, I guess, a little bit dubious, saying this is what we're working towards as technology gets better. But drinking water in the United States is very, very safe. Drinking water in Boston is tremendously safe. At the state level, the DEP, Department of Environmental Protection, they are able to make the regulations more stringent if they want to, but they can't relax them. So we have if you're interested, you can go on the US EPA website, the drinking water tab, you can see what they test for and what the quality of water is everywhere. So drinking water out of taps is very, very clean. I told you that Boston water is super clean. The only problem, though, is that some old buildings, there was lead pipes and lead solder that was used to bring water to your tap. So some old buildings can have elevated levels of lead. It has nothing to do with the water supply. It has to do with your plumbing. To get around any chance of lead, all you have to do is turn the tap on until the water runs cold. Then you know it's coming from the road. So point is, with regards to bottled water, Perrier, Evian, those are always really funny to me because they're bottled at the bottom of these mountains in France and elsewhere. And so you have these springs, the water's coming out of the bottom of the mountains, and they just bottle it. You don't do anything to it. But what they do on the mountains is they graze sheep and cattle there. So it's there's virtually no standard for bottled water. And a lot of times, all people are doing is bottling other people's tap water. Belmont Springs, you go to Belmont, Mass, and use their municipal water supply, put it in bottles and sell it to people. So it is very, very lax, the regulations for what you can provide in bottled water, which means that it's sometimes even more contaminated than tap water. So drinking water out of a fountain or faucet is the best. So I think that is